Hello students, welcome one and all. In the last class we have seen up till Mosley's periodic classification of elements, where the periodic law given was the physical and chemical properties of an element depend upon their atomic numbers. So I also told that there will be plenty of other types of classifications which are convenient for us. Bohr has given a classification, long form of periodic table, classifying the elements into various blocks. So all those we will be seeing today. But before entering into those types of classifications, let us begin with a small question. The question is, suppose an orbital may accommodate 3 electrons, then calculate the number of elements. So every orbital will accommodate only 2 electrons. You will come to know from the atomic structure, it can accommodate only 2 electrons. Supposing that if it is accommodating 3 electrons, then how many elements would be present in the first, second, third and fourth period? So we know that we have 2, 8, 8, 18, 18, 32 and 32 elements in the 7 periods. Okay, this is under normal conditions when every orbital can accommodate only 2 electrons. But now in the first period I have S orbital which is accommodating 2 electrons, therefore 2 elements are present in the first period, hydrogen and helium. Suppose if it is occupying 3 electrons, then the answer would be first period will occupy 3 electrons. Simple. Okay. Next, second and third period we have S and P. We have S and P subshell. So S and P would become 4 orbitals. Right? We have S and P. So altogether these are 4 orbitals. Each orbital will accommodate 2 electrons. Therefore we have 8 elements in the second period and third period. Now they are accommodating 3 electrons. So I give 4 into 3, 12 electrons. It means second period and third period will accommodate 12 electrons. 12 elements, because these are accommodating altogether 3 electrons per orbital. Therefore 12 elements will be there in the second period and third period instead of 8 elements in the second and third. Fourth period, generally it will have 18 elements, but supposing that it is occupying 3 electrons per orbital, then in the fourth period we have S, P and D also. 1 S orbital, 3 P orbitals, 5 D orbitals, altogether making it 9. Each orbital is taking up 3 electrons now. Therefore it will be 27 elements in the fourth period. So it has to accommodate 27 elements. Right? So we got the answer. 2, 8, 8, 18 is the normal occupancy of the elements of first, second, third and fourth periods. If at all each orbital can accommodate 3 electrons, then it would be 3, 12, 12 and 27. Okay, that is the answer. So let us move to the next type of classification. We said different types of classifications are there. One type of classification we call it as Bohr's classification. How did Bohr classify all the elements of the periodic table? This is one of the simplest classifications. He classified all the elements into 4 types. One type he called it as inert gases. One he called it as representative elements. One he called it as transition elements. And one classification he called it as inner transition elements. So altogether there are 4 types. Okay. Inert gases, representative elements, transition elements and inner transition elements. Representative elements are also called as normal elements because these are very regularly found, therefore they were called as normal elements, or they were like representatives, therefore they were called as representative elements. So for each of this classification, what are the important points, we'll just see. But the basis of the classification is very simple. What is the basis for the classification? Suppose that I take an atom. In the atom we have nucleus, and in the nucleus we have different shells. Okay. The last shell is called as ultimate shell. or the valence shell. Okay, the valence shell. The next one to the ultimate, we call it as penultimate shell. Ultimate or valency shell, penultimate shell, and one before to that we call it as anti-penultimate shell. Not anti, it is anti-penultimate shell. So the first or the last shell from the nucleus we call it as valency shell or the ultimate shell. The next one is called as penultimate shell. The one next to that is called as anti-penultimate shell. Okay, that one before penultimate shell is called as ante. Opposite to ante is post. Just like we have AM, PM, ante-meridian and post-meridian. Here also we have ante-penultimate shell, before penultimate shell. Okay. If the ultimate shell or the valency shell is completely occupied, if it is complete, then those elements fall under inert gases. Simple way. Okay, very simple way. If the valency shell is complete, they come under inert gases. Or if the valence shell is complete, you can also call it as valence shell. If it is complete, they come under inert gases. If the valence shell is incomplete, they fall under representative elements. Valence shell, if it is complete, inert gases. If the valence shell is incomplete, representative elements. If the valence shell and penultimate shell are incomplete, we call them as transition elements. If the valence shell, penultimate and anti-penultimate shell are incomplete, we call it as inner transition elements. Very simple. Okay. So ultimate or valence shell complete, inert gases. Valence shell incomplete, representative elements. Valence shell and penultimate shell incomplete, transition elements. Valence shell, penultimate and anti-penultimate shell incomplete, we call it as inner transition elements. Okay. So just one or two points we'll see about these elements. The first one is inert gases. Generally we call them as inert gases. We also have another name for it. We call them as noble gases. What is the reason? I'll just explain. So these are some important points. Inert gases. Valence s and p orbitals are fully filled. The valence shells are fully filled. For helium, if I choose, it is S. And for the other inert gases like neon, argon, krypton, xenon, radon and argon Sn, it is S and P, which are the valence shell. So they are fully filled. Valence orbitals are fully filled. Right? How many elements are there? Altogether we have helium, neon, argon, krypton, xenon, radon and argon Sn. Altogether there are 7 elements in the inert gases. These are highly unreactive. They are very unreactive, but under normal conditions. But under abnormal conditions, some of these compounds can also react. One of the best examples is xenon. When we discuss about chemical bonding, in chemical bonding and VSEPR theory, we'll see plenty of xenon compounds. We have to get the structures of xenon compounds. So xenon can form oxides, xenon can form fluorides, xenon can form oxyfluorides. So plenty of xenon compounds are there. Therefore, instead of saying them as inert gases, we gave a name called as noble gases. Okay, we call them as excuse me, we call them as noble gases. One more important point, let it be John Newland's octaves, law of octaves. There was no known inert gases at that time. Even Mendeleev, when he started classification of elements, inert gases were not known. Later on he included into his periodic table when these inert gases were discovered. So in the beginning it was not there, even in the Mendeleev's periodic table. Later it was included. That is second point. And third point is, these are the end elements of each period. Suppose if I consider first period, helium is the end element. Second period, neon is the end element, and so on. So these are the end elements of every period. You remember that point. Inert gases are the end elements of every period. Completely filled shell is present in it. Okay. No shell is incomplete. These are also called as noble gases. There are 7 elements altogether. These are just a few important points about inert gases. Next we have representative or normal elements. First striking feature that you have to remember is valence shell is incomplete. Valence shell is incomplete. That is the most important point. These are representative elements, most commonly found elements. Number of electrons can vary from 1 to 7. 8 will not be filled because s and p orbital altogether it will make 4 orbitals. 4 into 2 8 electrons, but it should be incomplete. Therefore to the maximum we can go up to 7 electrons only. These are very active metals and therefore these were called as representative elements. They are very abundant and very active. Okay, simple classification. When we go to SPDF, then we will give more points. Third one, transition elements. In transition elements I told you valence shell as well as penultimate shell both will be incomplete. So if I take penultimate shell, for ultimate shell we give ns, for penultimate shell we give n minus 1, for anti-penultimate shell we give n minus 2, where n is the principal quantum number. Suppose if I have 4s, then the penultimate shell would be 3d. Suppose I have 5s, 4d, then we have 3f. But do you have 3f? No. 3f will be beginning from 4f. So if you have 4f, 5d and 6s, so it will be beginning with 6th s. Okay, if you have 6s, then you can have 5d, then you will have 4f. For 5s there is no 3f. Okay, so remember this point. When you have 6s, then you can have 5d, then you will be having 4f. Right. So here we said valence shell and penultimate shell are incomplete. So the penultimate shell we have tried it as n minus 1 d 1 to 9 only. Don't fill it up to 1 to 10, because if it is 1 to 10 it is not a transition element. It should be incomplete. N minus 1 d 1 to 9, and ns could be either 0 or 1 or 2 in their ground or excited state. Let it be in their ground state, in their normal state, or let it be in their excited state. The electronic configuration has to be n minus 1 d 1 to 9, ns 0, 1 or 2. Okay, these are the electronic configurations that was given by Bohr. And how many elements are there? So in every series, if I consider, there will be only 9 elements, because to the maximum I can fill up to 9 electrons. So there will be only 9 elements. Suppose if I start from scandium, I begin from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel and copper. Till copper I have to stop, because zinc has fully filled shell. Zinc will have D10. So zinc, cadmium, mercury, copernicium, they don't fall under transition elements according to Bohr's classification. Okay, this is an important point to remember. I repeat that point. Zinc, cadmium, mercury and copernicium, they don't fall under transition elements because they have fully filled D shell. All our metals in the beginning also we discussed. S block are totally metals, D block are completely metals, F block are completely metals. Only P block we have metals, non-metals as well as metalloids. Then the last one is inner transition elements. Inner transition elements where the valence, penultimate and anti-penultimate shells are incomplete. So when I say incomplete, the configuration given is n minus 2 f 1 to 14. Remember this point, 1 to 14. If it is 1 to 14, it is looking like complete. Okay, so remember this point. N minus 2 f 1 to 14, n minus 1 d 0 1 and ns2. N minus 1 d 0 and 1. You are not going up to d9 or d10. So d should be either 0 or 1. 0 or 1. Remember, for F block elements, d 0 or 1. ns 2. So ns will be 2, but n minus 1 d could be 0 or it could be 1 electron. N minus 2 f can be 1 to 14. Now immediately you will be getting a doubt. 1 to 14, it is a fully filled shell. Let us check. There are two series of it. One is called as lanthanides or lanthanoids or lanthanones, actinides or actinoids and actinones. Lanthanides, in the beginning class we have seen, it will begin from cerium to lutetium, and actinides begin from thorium to lawrencium. All actinides are radioactive, and from 93 they are called as transuranic elements. All are the synthetically prepared man-made elements. We call them as they are prepared in the lab. They are not naturally available elements. Well, here you remember one important limitation. Previously in the transition elements, n minus 1 d up till 9 only. So where is the place for zinc, cadmium and mercury? Where should I place them? Zinc, cadmium and mercury. There was no answer for Bohr. That is a severe limitation of Bohr's classification. So here I have given that point. Zinc, cadmium and mercury were not included anywhere according to Bohr's classification. Next, when I say antepenultimate shell should also be incomplete, if antepenultimate shell should be incomplete, then why should I include lutetium and lawrencium? Because they have fully filled shells. If I have included lutetium and lawrencium, then I should say the n-2 shell, antepenultimate shell, must be filled up. But in this case, lutetium and lawrencium are filled up, but they have given it as antepenultimate shells are incomplete. So that is not properly justified. Right? In the last I have given, inclusion of lutetium and lawrencium in the inner transition group is not properly justified since their shells are fully filled. So two important limitations we have for Bohr's classification. One limitation is zinc, cadmium and mercury has no place because they are fully filled shells. Second important limitation is lutetium and lawrencium, they are fully filled shells. But in the beginning we called them as incompletely filled shells. Inner transition elements will have antepenultimate incomplete shell, but they have got fully filled shell, lawrencium and lutetium. Therefore their inclusion is not justified. So even this classification is not giving a complete picture. There are some limitations of this classification. Okay, so let us move to the next classification. The next classification is differentiating electron classification. One of the most commonly used classification, we call it as differentiating electron classification. What is this differentiating electron classification? When I say differentiating electron, it is nothing but the last electron. Whatever last electron that is present, that is called as a differentiating electron. Differentiating electron means last electron. If I take, say, sodium, 1s2, 2s2, 2p6, 3s1. So 3s1, that is the last electron. Where is the last electron entering into? It is entering into third shell and s subshell, s orbital. It is entering into s orbital, 3s. Since it is entering into s orbital, it is the last electron. Forget about 1s2, 2s2, 2p6, 3s1. Where is the last electron entering? Based on that, this classification has been given. So if the last electron, which is the differentiating electron, if it is entering into s orbital, I call it as a s block element. If the differentiating electron is entering into p orbital, suppose if I take oxygen, 1s2, 2s2, 2p4. So that last electron is filling 2p1, 2p2, 2p3, 2p4. The last electron is filling into p subshell. Therefore we are calling it as a p block element. And if the last electron is filling into d orbital, d block, and if it is filling into f orbital, we call it as f block elements. Very simple. So where is the last electron, which is called as a differentiating electron, entering into which orbital? Based on that, this classification has been given. This is a very convenient classification. We classified them into 4 blocks: s block, p block, d block and f block. So for each of these, just let us go through the electron configurations and what are the most important striking features or the characters of these blocks. We'll just go through easily. Okay. First one, we call it as s block element. As I told you, the last electron will be entering into s orbital. Therefore all these elements are classified under s block. When I say s block, it is the beginning block. Or if I take a look at the periodic table, we have the left portion, we have the middle portion, right portion and the bottom portion. So for your side, left portion is your s block, middle portion is the transition element, right portion is the p block, and the down portion, bottom portion will be f block. S block, there are only 2 groups. There are only 2 groups. There are 2 different types of classifications. One we call it as American style, the another is called as IUPAC style. In American style, we have A and B type of methods: 1A, 2A, 3A, 4A and so on. In 1A, 2A, and also you have 1B, 2B and so on. But in IUPAC, you have direct numbering. Starting from 1, you end with 18. 1, 2, 3, 4, 5 up till 18. Those are the number of groups. But in American style we have A and B type of classifications. Okay. So here in S block we have two groups. One group we call it as 1A, second group we call it as 2A group. 1A and 2A. We have to use Roman numerals only. We have to use Roman numerals for 1A or 2A. So here I have given 1A and 2A groups. Each of these groups are given a separate name. This in detail we have to discuss under groups. Whenever we discuss the block elements, S block or P block elements, then we have to separately discuss why the name has been given, what are their properties. But this is only periodic table of elements, chemical periodicity, only basics will be given here. Okay. So there are two groups. One we call it as alkali metals, the another one we call it as alkaline earth metals. Both of them are metals. That is first important point to remember. Next point, these elements are highly reactive. These are the beginning elements. 1A, these are the beginning elements of each period. Later comes 2A. So 1A as well as 2A, they come under highly reactive metals. These are soft metals. They are not hard metals. They are very soft metals. They are so soft that I can even cut with a knife. Suppose I take sodium. You will be doing some practical laboratory experiments also, where if I want to handle sodium, sodium is a metal, but I can take sodium just with a small blade also we can cut, not even a knife. I can take a blade, and with a blade I can cut sodium. So these metals are so soft that we can even cut with a knife or a blade. Second point, these metals, they have some luster. Luster means they are little bit shinier, but they very soon they get tarnished. Tarnished in the sense they immediately get reaction with oxygen, they form some oxide layer, so it gets tarnished. Suppose if I take sodium, sodium will not be fresh. Whenever I keep it for a long time, it will be like tarnished and it will be like a gray color over the sodium. If you cut that gray color layer, then you will be seeing that fresh sodium. Okay, that is one point to be remembered. Second point about conductivity. Electrical conductivity and thermal conductivity. When I compare it with D block elements, transition elements, their conductivity is compared to be low. But what is most striking feature is these S block elements, these are the beginning elements. Right? These are the beginning elements. So when I say beginning elements, just suppose I am giving you the blocks. Imagine I have given you S block, D block, P block and F block. Since these are the beginning elements, their electropositivity will be very high. Electropositivity will be very high for these elements. They have a fixed oxidation state. Suppose if I take alkali metals, the alkali metals fixed oxidation state will be +1. You don't find variable oxidation states. Suppose if I choose iron, iron can have +2, +3, +4. Variable oxidation states are present. Copper can have +1, +2, +3, +4, variable oxidation states. But most commonly, copper can have +1, +2, +3, +4 are rare. Iron can have +2, +3, +4, +5 are rare. Okay, there are some rare oxidation states, common oxidation states, but for this there is only one oxidation state, which is +1. There is an exception which will come later at an advanced level, but under normal conditions for alkali metals the common oxidation state is +1. For alkaline earth metals the common oxidation state is +2. Suppose if I take calcium, its oxidation state will be +2. You don't see calcium existing in +1. You don't see sodium existing in +2. You see sodium, potassium existing in +1 only. Okay, so that is alkali metals and alkaline earth metals. They are highly reactive, highly electropositive. They are ready to lose electron. Since they are so electropositive, they are ready to lose electron. When they are ready to lose electron, we call them as very strong reducing agent. They have very high negative potentials. Since they have very high negative potentials, we call them as strong reducing agents. Okay, so 1A and 2A group elements are very strong reducing agents. They are so strong that suppose if I put them in water, they are so strong, they react so fastly that immediately hydrogen will be released, and most of the times these reactions are exothermic. The release of hydrogen is so exothermic that you will find fire. Immediately it will catch fire. So you can just watch any YouTube video also. You take some sodium, put it under water. Don't do it on your own, getting sodium, it is very dangerous. If you just put sodium in water, immediately it will catch fire. If the quantity is very low, then fire cannot be seen. There will be a little, what do you call, blast like. But if you take more sodium, then fire is also seen. So you have to be very careful while handling these elements. They are highly reactive. They are highly reducing also. Their reduction power is very, very high. Okay. Now these are in the left hand, and when in the right hand, if I take oxygen, these elements can form oxides. They also form hydroxides. When we go to the physical properties and chemical properties, when we go to the trends, when we go to the physical property trends like electron affinity, electronegativity and so on, we see that when they combine with oxygen, electronegativity difference will be large. Between an S block and an oxygen, electronegativity difference will be large. So most of these oxides are found to be basic in nature. Most of the 1A and 2A group oxides are basic in nature. If I consider P block elements, if they form oxides, they will be mostly acidic in nature because the electronegativity difference will be small. But when I consider an oxide forming from S block, then they are basic in nature. Okay. They also form hydroxides. Hydroxides are alkaline in nature. Oxides are basic in nature, hydroxides are alkaline in nature. They are highly electropositive elements. Cesium is found to be the most electropositive because down the group electropositivity increases. We have to discuss the trends also once we complete the classifications. Right? I'll just show you a few important points about the S block elements. Here are the important points. They show a fixed valency, very low melting and boiling points, low ionization energy. Ionization energy is very low. I said they are very highly electropositive. Highly electropositive means ionization energy is found to be very low. They are ready to lose electron. Since they are ready to lose electron, they are considered to be highly reducing in nature. They are good conductors of heat and electricity, but thermal conductivity, when I compare it with the D block elements, it is not that high. Okay, but they are good conductors of heat and electricity because they are metals. Since they are metals, they are always good conductors of heat and electricity. Possess largest atomic radius in their corresponding, because these are the first elements, they have the largest atomic radius. Very reactive and readily form ionic compounds. Instead of forming covalent compounds, these are ready to form ionic compounds. Why are they ready to form ionic compounds? Because they are ready to lose electrons. If there is some other element which can gain electron, it can easily form ionic compound. So covalent compounds are very rare, except with beryllium, because beryllium is very small. So beryllium you can find to be forming some covalent compounds. These are never found in free state. Because they are so reactive, they are never found in free state. They are found in combined state in the nature. Okay, that is one more point to remember. Strong reducing agents. I cannot prepare alkali and alkaline earth metals by doing electrolysis of their aqueous solutions. Why can't I prepare? Because if I want to do electrolysis process, it will release hydrogen. Instead of getting sodium deposited, you will be getting hydrogen liberated, because they are so strong reducing agents. So I just cannot prepare these metals through the process of electrolysis. Okay. Except beryllium and magnesium, they impart characteristic color to the flame. We will see in the 1A group and 2A group elements. For each element there is a characteristic flame color, where you can easily identify, if I get apple green, what is the element, or if I get a brick red color, what is the element. So there is ignition test also, ignition test, or you can call it as flame test. Compounds of S block elements are predominantly ionic, and according to Fazans, we will come to know, according to Fazans, most of the ionic compounds are colorless. Not all, most of the ionic compounds are colorless. Most of the covalent compounds will be colored. Not all, most of the covalent compounds will be colored. Lithium and beryllium compounds are covalent in nature. I told you when they are very small, lithium is very small in the 1a group element, beryllium is also very small in 1a group elements, so they have a tendency to form covalent compounds. Atomic size is very small, they are ready to polarize the anion to a greater extent, and due to this polarization, overlapping will be large, covalency will be large, then it will lead to covalent compounds. Okay, we have to see it in the trends. They have greater affinity for oxygen and non-metals because these are in the left side, so they have a greater affinity towards the elements that are present in the right side. Oxides are basic, hydroxides are strongly alkaline. They displace hydrogen from acids. Suppose if I take HCl and if I react sodium chloride, or if I take some other acid, they immediately displace hydrogen from those acids. Decompose water and readily evolve hydrogen. Okay, but here one important point you remember in the last one, they decompose water and readily evolve hydrogen except beryllium and magnesium. Except beryllium and magnesium. So I take some other elements, I put it under water, they displace hydrogen from that except beryllium and magnesium. Okay, remember these two elements. Lithium, why do you remember lithium and beryllium for? Lithium and beryllium you are remembering for covalent compounds. Beryllium and magnesium you are remembering for exceptions where they don't release hydrogen. They don't evolve hydrogen when reacting with water. Right. So S block elements, important characteristic features are completed. All this you should be aware of. What are the characteristic features? Individually we will study under the groups, but this is like a gross study. Just we are studying what are the various types of properties of each block, what are the various trends across a period and a group of the physical properties. All these things we have to study under periodic classification of the elements. We are also seeing all the different types of classifications. Come to the p block elements. So in the beginning I told you, when a differentiating or the last electron is entering into p orbital, we call it as p block element. P block element, we have variable oxidation states. This is the most striking feature of p block elements. These were also called as representative elements under Bohr's classification. Representative elements. For p block elements, the what you call valence shell is incomplete. Valence shell will be incomplete. I can fill up to 7 electrons. One important feature of p block elements is you can find metals, you can find non-metals, you can also find metalloids. Okay, if I go for S block, purely metals, D block, purely metals, F block, purely metals, but P block has got metals, all metalloids and all non-metals are present only in P block. Okay, and I told you they have variable oxidation states ranging from n to n minus 8. What is this n to n minus 8? Suppose if I am considering 3A group of element, this is old classification, 3A, 4A, 5A, 6A and 7A. For 3A, commonly the oxidation state is plus 3. But when I go to 4A, n up to n minus 8, suppose it is existing in plus 4 oxidation state. Plus 4 minus 8, it is minus 4. So there could be an oxidation state range from plus 4 to minus 4. Okay, so variable oxidation states can be seen. If I take a simple example of carbon, you will see in the organic chemistry also, carbon can have plus 4 oxidation state, carbon can have minus 4 oxidation state also. That depends on what type of element it is combining with. So carbon can have plus 4, carbon can also have minus 4. We'll see different examples also. Later 5A, plus 5 and plus 5 minus 8 is minus 3. So plus 5 up to minus 3. Plus 6 up to minus 2, plus 7 up to minus 1. One classical example we see for 7A, these are Halley's acids. Hypohallous acids, plus 1, Halley's acids, plus 3, Halleic acid, plus 5, perhallic acid, plus 7 oxidation states can be seen. Okay, so we have to discuss under halogens. Whenever we discuss halogens, we have to go through all these compounds. Hypohallous, Halley's, Halleic and perhallic. Plus 1, plus 3, plus 5 and plus 7 oxidation states. So when I say chlorine or when I say bromine, they just don't exist only in one oxidation state. They can be found in variable oxidation states. That is the importance of p block elements. Okay. So before going to the next topic, a very small question. What is the oxidation state of oxygen in the following compounds? Oxygen belong to P block. Oxygen belong to P block. What is the oxidation state of oxygen in the following compounds? Oxygen is a non-innocent ligand. There are different types of classifications, right, which I will discuss in the coordination chemistry. There are different types of classifications of ligands. One type of classification is innocent ligands, non-innocent ligands. Innocent ligand means, suppose fluorine is present. Fluorine belongs to P block. It has a fixed oxidation state. We can't say variable oxidation state because it belongs to P block. No, it belongs to halogen, fine, but it has a fixed oxidation state of -1 only. There is no other oxidation state for it. But if I go for chlorine or bromine, then oxidation states can change. But fluorine has a fixed oxidation state. Okay, so fluorine becomes an innocent ligand. But suppose if I take oxygen, oxygen is generally called as a non-innocent ligand. Non-innocent ligand means it will not allow you to calculate the oxidation state of the metal when it is combining with that. So you have to be very careful whenever you are calculating oxidation state of the metal when it is combined with oxygen. You just go through the question and try to attempt. Oxygen, when it is found as oxide, it can have 2 minus. When it is simply found in O2 elemental state, 0. Or it could be O2 minus, or it could be O2 2 minus. This is called as superoxo. This is called as peroxo. This is called as dioxygen. This is called as oxide or oxido. So oxido will carry 2 minus. O2 in its elemental form in the sense in its natural state, it has 0, but it can take 1 electron converting into superoxo, it can take 2 electron converting into peroxo. So whenever I give O2, in which form is it existing, we cannot say. That is not easy. That is why we call it as non-innocent ligand. Non-innocent ligand. Okay, but anyway, this is a easy question for you because potassium, it has fixed oxidation state. So potassium is +1. Potassium is +1. It is having fixed oxidation state. So O2 should have -1 because it is a compound which is neutral. There is no charge for the compound. So if potassium has +1, O2 should have -1. O2 should have -1, then what is the oxidation state of each oxygen? -1 for 2 oxygens. So each oxygen will have -1/2. That is the answer. The question asked is what is the oxidation state of oxygen in these compounds? So the oxidation state of oxygen is -1/2 because there are 2 oxygens which are sharing -1 oxidation state. So each oxygen will have -1/2 oxidation state. So based on this, I think you can very easily answer the second one. This is +1, so this should be -1. -1 over 3 oxygens, so each oxygen should have -1/3. Third one is very important for coordination chemistry also. For IUPAC nomenclature also it is very important. Why it is so important, I'll tell you. O2PtF6. Fluorine, we have fixed oxidation state, it is -1. So we have 6 negative charges. When we have 6 negative charges, there should be 6 positive charges. 6 into -1 is -6. 6 negative charges are present. There should be 6 positive charges also. Okay. So when we have 6 positive charges, that should be distributed between platinum and oxygen. We know that common oxidation state of platinum is either +2 or +4. The other oxidation states are very rare. So either I find platinum in +2 or I can find platinum in +4. If I find platinum in +2, oxygen should have +4. Because this is 6 negatives, we should get 6 positives. If platinum is plus 2, oxygen should be plus 4. Ruled out. If platinum is plus 2, if platinum is plus 4, oxygen should be plus 2. I am getting a doubt. Oxygen is getting plus 2, plus 4. Is it possible? Because oxygen is one of the more electronegative atoms. On the electronegativity scale, it has a value of 3.5. When it has a value of 3.5, can it get a positive charge? Is it possible? Because just now I gave different charges like 2 minus, minus 1 and so on. Or it could be 0 also. But can it have a positive oxidation state? That is our question. The answer is yes. This is one rare compound where oxygen can have positive oxidation state. Okay, this is actually O2 PTF6. It is a coordination compound. So for a coordination compound, we begin with cationic part following with anionic part. Here the cationic part is O2, anionic part is PTF6. This is a very rare compound where we see platinum to be present in plus 5 oxidation state. Plus 5. So 6 negative charges, 5 positive charges on platinum. So this should carry plus 1. O2 is carrying plus 1. So each oxygen should have plus 1 by 2. Hope you are getting my point. There are 6 negative charges. There should be 6 positive charges. Platinum was found to have plus 5 oxidation state, which is very rare. Then O2 should have plus 1 oxidation state. O2 should have plus 1, so each oxygen will share plus half oxidation state. Plus half will become plus 1. So O2 carrying plus 1, platinum carrying plus 5, fluorine, each fluorine carrying minus 1. This is a very rare compound. Heavier metal hexafluorides are very, very strong oxidizing agents. How strong oxidizing agents are they? Then the answer is here. Heavier metal hexafluorides, platinum hexafluoride, they are so strong oxidizing agents that they can even oxidize oxygen. Oxygen itself will oxidize everything else, but this is so strong that it can even oxidize oxygen and it can remove electron from oxygen, converting it into O2+. Okay, and this compound, as per the IUPAC nomenclature, we call it as dioxyzenyl. Then we have to give some space because cationic part is completed. Then we have to start with anionic part. In anionic part, everything should be written without any space. Hexafluorido. Anionic part should end with 8 and the oxidation state is plus 5. It is written in Roman numeral 5 enclosed in parenthesis. So this is the IUPAC nomenclature of O2 PTF6. We call it as dioxyzenyl, give some space and then write without space hexafluoridoplatinate 5. Okay. Right. So let us look at general trend. This trend we will be seeing when we move on to the next type of classification also across the period and down the group, what is happening to non-metallic character. This separately we'll see. Okay. So I'm not stressing on this. And when it comes to oxides, I told S block elements will form basic oxides. P block elements, where the electronegativity difference between the oxygen and the combining element is smaller, they form acidic oxide. Greater the electronegativity difference between oxygen and the combining element, greater is the basicity. Lesser the electronegativity difference, greater is the acidity. Simple logic to remember. And coming to D block. D block, we have altogether 4 D series. I told you these are also called as transition metals, but when I say transition metals, zinc, cadmium, mercury must not be included. Remember, zinc, cadmium, mercury are not coming under transition elements. They have fully filled shells. But in the inorganic chemistry, interchangeably we use the word transition elements even for D block elements. So don't get confused. Transition elements and D block elements are interchangeably used terminology. Precisely speaking, zinc, cadmium, mercury are d block elements. They are not transition elements. Remaining elements are transition elements. Okay, so just remember this point for the future classes. The differentiating electron enters into n-1 d subshell, which enters into penultimate shell and incomplete subshell. Okay, if it is a transition element, we have altogether 4 different series: 3d series, 4d series, 5d series and 6d series. 3d series will begin from scandium ending with zinc, 4d series starting with yttrium ending with cadmium, 5d series starting with lanthanum ending with mercury, and 6d series starting with actinium ending with copernicium. So scandium, yttrium, lanthanum, actinium, zinc, cadmium, mercury and copernicium. You have to remember these elements: scandium, yttrium, lanthanum, actinium, zinc, cadmium, mercury, copernicium. Copernicium will have atomic number of 112. Okay. What are the common features? All of these are metals. First point to remember, all of these are metals. Second point to remember, they are very highly conducting. They are thermal conductors. They are also electrical conductors. They are ductile and malleable. We can convert them into wires and sheets. They are hard metals. They are not soft metals. They are hard metals. And when it comes to electropositivity, they are not as electropositive as S block elements. They are electropositive, but not as much as the S block elements. Okay, so these are hard in nature, not soft. These are hard in nature, malleable and ductile, because we can easily convert them into wires and sheets. Good conductors of heat and electricity. Densities are very high. Why are the densities very high? We'll discuss when we go to the trends. Because more number of protons as they add up, lanthanide contraction is also there. Due to lanthanide contraction, densities are found to be very, very high. And densities are high, their atomic sizes are almost the same, therefore very easily they can form alloys. So d block elements can easily form alloys. Platinum, gold and mercury are called inert elements. These are inert under normal conditions. Under extreme conditions they react, but under normal conditions we call them as noble metals, because they are highly unreactive under normal conditions. They show variable valency. When I say variable valency, I can have +1, +2, +3, +4. I can even go to +8 oxidation state. If I take osmium tetroxide, osmium is found to be present in osmium is found to be present in +8 oxidation state. It is combining with 4 oxygens. So osmium can have +8 oxidation state to the maximum, or it can have +1 oxidation state also. Okay, so we call it as variable oxidation states. But most common oxidation states are +2 and +3. Most of the compounds are colored and paramagnetic. They are colored and paramagnetic because these are ready to form complexes, coordinate complexes. They can form ionic complexes, they can form covalent complexes, they can form coordinate covalent complexes also. When I consider S block, they mostly form ionic compounds. When I consider P block, they mostly form covalent compounds. When I consider D block, they can form all these types: ionic, covalent, coordinate covalent also. Coordinate covalent is like a combination of ionic and covalent. They can act as good catalyst. Whenever I say good catalyst, there should be some coordinative unsaturation in the metal. It should be readily able to switch on its coordination number, coordination geometry and oxidation state. So if it is ready to switch on their oxidation state, coordination number and coordination geometry, they can better act as catalyst. And all these three things can be done by transition elements or the D block elements. Not exactly D block elements, transition elements, and hence they can act as good catalyst. Zinc, cadmium and mercury have fixed oxidation states, so we have to be very careful with them. They act as good catalysts. They have high tendency to form complex compounds, coordination compounds. That is a separate unit we have to discuss. High tendency to form alloys because their sizes are almost similar because of lanthanide contraction and very high density. They form both ionic and covalent compounds. Finally, coming to F block elements, these are the inner transition elements. They have some similarities with the transition elements, therefore we call them as inner transition elements. There are two series. One we call it as lanthanoids or lanthanides or lanthanones. The other we call it as actinoids or actinides or actinones. All of these are metals. They can also form colored complexes. They can also form paramagnetic complexes. What are paramagnetic complexes? What is the nature of the color we will come to know in D block elements. When we separately take D block, there you will come to know. F block, there you will come to know. Okay, this is only just an introductory part. They have different oxidation states ranging from +1, +2, +3, +4, +5. It can have various oxidation states, but the most common oxidation state is +3. Along with +3 you can also find +2, +4, but +3 is the most common oxidation state. Even F block elements have got a tendency to form complexes. Though the number of complexes formed by F block elements are less, but they also have a very good tendency to form complexes. And when it comes to actinides, they are radioactive. Okay. So this is the classification about the given metals, whatever elements that we have taken. We have taken Bohr's classification. Bohr has classified into 4 different groups: inert gases, representative elements, transition elements, and inert transition elements. Later on we have taken up block classification: S block, P block, D block, and F block. And finally we will conclude this session with simple questions, with few questions. What are these questions? The element having electronic configuration: krypton 4d10, 4f14, 5s2, 5p6, 5d1, 6s2 belongs to which block? It belongs to which block? Just for each question you take a little time, try to attempt, or you can pause the video and then attempt, and then you can check. Element having electronic configuration. Look at the valence shell and penultimate shell. This is 5d1, 6s2, 5d1, 6s2, so it has to belong to D block. 5d1, 5d2, 5d3, 5d4 with 6s2, all of them should belong to D block. n-1d 1 to 9 or n-1d 1 to 10 ns2, that should belong to D block. So the answer is D block element. Forget about the beginning configuration. Look at the valence shell. Based on that, you just put where the last electron is entering into. That is entering into D orbital. Therefore, it belongs to D block. Which of the following represents the electronic configuration of D block elements? Again, this is very simple. When I say D block elements, that should have ns2, ns0, 2, and n-1d 1 to 10. So here we have n-1s nd, wrong. n-1d ns, this is right. n-1d ns, again p, no. n-1p and ns, no. P and s will have same quantum number, n will be same for them. Here n-1d and ns will come, but again p will not come here. So the option is n-1d 1 to 10, ns 1 to 2. B is your option because it belongs to D block. Valence shell n, penultimate shell should be n-1. The element whose electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 is metalloid, noble gas, non-metal, or a metal. The simple way, you look at the valence shell: 3d10, 4s2, 3d10, 4s2. 3d10 means it belongs to D block. All D block elements are metals. So the option is metal. And what could be the metal? 1s2, 2s2, 2p6, 6, 7, 8, 9, 10, 18, 20, 30. So 30 means that metal is zinc. The element whose electron configuration, I think just now we have done it. Right. The element with atomic number 106 will be an element of S block, P block, D block, or F block. Just take some time. The element with Z equal to 106 will be an element of S element, or is it P block, or is it D block element, or is it F block element. 106 is seaborgium. Directly you can say it belongs to D block without any confusion. But how to know? Just I'll give you a simple logic. The logic is, whenever the elements are beyond 104, 104 and beyond 104. Okay. Whatever element number that has been given, that element number you subtract from 82. You just subtract from 82. 82, you just remember this figure. This is a logical number. So let it be 106, 107, 108, 109, 110 up till 118. Whatever element that has been given to you, you subtract it from 82. So when I subtract it from 82, how much do I get? 24. 24 is chromium, right? So it belongs to chromium group. When it belongs to chromium group, that has to be a D block element. It is, you are getting 24. It means you are getting chromium, molybdenum, tungsten, seaborgium. It means that should belong to D block. So whatever elements that are given beyond 104 up till 118, simply subtract them from 82. Okay, this is the logical number. When you subtract them from 82, you will be getting an element present in that particular block, and based on that you can say to which block does it belong to. That is simple logic. The electronic configuration of few elements are given below. From the above electronic configurations, predict which one is so and so. Okay, I think this I am leaving it for you. It is a very simple one. You can very easily do it, I guess. 1s2, 2s2, 2p6, 3s2. 1s2, 2s2, 2p6, 3s2. So this should be a S block element. In S block element, we have only two series. One is alkali, one is alkaline earth metal. Alkali metal, 1 electron. Alkaline earth metal, 2 electron. S1 alkali, S2 alkaline. S1 1a, S2 2a. So this should belong to 2a group. An alkaline earth metal. So this is an alkaline earth metal. This should belong to 2. A with 2. 1s2, 2s2, 2p5, ns2, np5. This has to be a halogen. ns2, np5 halogen, 7th group. Remember, ns2, np5 halogen, 7th group. 1s2, 2s2, 2p6, 3s2, 3p2. 3s2, 3p2. How many electrons are there in the valency shell? 4 electrons. So it belongs to 4th group. 4 electrons are there in the valence shell. It belongs to 4th group. 1s2, 2s2, 2p3. 5 electrons are there in the valence shell. Therefore it belongs to 5th group. 6th one. Okay, it belongs to 5th group. Next, 1s2, 2s2, 2p6, 3s2, 3p6. Totally filled configuration. Therefore it has to be a noble gas element. 3. And the last one left out is 3d2, 4s2 transition element. So this should be with 5. Okay, so look at the valence shell. Based on that you can get some analysis. The valence shell electronic structure of an element is ns2, np5. The element belongs to the group of halogen. Just now we have worked out. Which one of the following group contains metals, non-metals as well as metalloids? That group should have metals, non-metals and metalloids. It means that group should be of p block elements. 1a, 2a are s block elements, purely metals. Forget about it. 7a, 8a, all 8a are halogens. Fluorine, chlorine, bromine, iodine and astatine. There is no metalloid. Astatine, it is considered as a metalloid, but it should also have non-metals as well as metalloids. So astatine, it is like a controversy. Some give it as a metalloid, some don't give it as a metalloid. So forget about 7a group. Come to 4a. Carbon, silicon, germanium, tin, lead. Carbon, non-metal, germanium, silicon, metalloid, tin, lead, metals. So the option is 4a. Okay, right. So here in this session what we have learnt is two different types of classifications of the elements, how to classify them and what are their basic characters, Bohr's classification and differentiating electron classification SPDF. In the next session we will be seeing long form of periodic table, where we will conclude how the elements are being classified into how many groups and how many periods. Each period has how many elements, what is the general electron configuration, or how many orbitals will be there for each period. All these things we'll see. Later we have to move to the general trends of the various physical properties like electron affinity, electron negativity, atomic atomic radius, ionic radius, shielding effect. All these things we have to see in the coming sessions. Okay, but my sincere request is keep revising whatever topic that has been completed, along with the topics which were done in the previous sessions, along with the questions that I'm working out. Try to work out all these things, right? I wish you all the best.